A matrix is simply an array of numbers arranged in a certain fashion. Now, one source for this array of numbers is a system of equations. For example, take this system of equations. And actually, there are two matrices that may emerge from this system. One is called the coefficient matrix. A coefficient matrix is an array of numbers that corresponds to the coefficients involved on the x's and y's and z's in our system of equations. Another matrix that comes from this system is called an augmented matrix. It's nothing more than the coefficient matrix. You see, these entries and these are exactly the same, along with the constants involved in our system of equations. A lot of times a little dotted segment is drawn here to indicate the separation between coefficients and constants when using an augmented matrix. Well, let's talk generally about the matrix format here, and then we'll begin to work with the matrix. A matrix is this arrangement of numbers in a particular array, this sort of rectangular array that we've just seen. And we notice that there are rows and columns involved in a matrix. And the order of a matrix is given by the number of rows by the number of columns. An m by n matrix means some m number of rows by some n number of columns. Back over here, this matrix has, let's see, 1, 2, 3 rows, 1, 2, 3 columns. So this is a 3 by 3 matrix, and sometimes it would be called a square matrix, you see, because the rows and columns, the column number, row number are the same. This one is 3 rows by 4 columns, so it's a 3 by 4 matrix. Now, the entries involved in a matrix are designated often like this. The entry, which is A subscript 1, 3, means the entry that is in the first row, third column. You see the first item here in this subscript, the first digit designates a row number, and the second digit a column number. So in this way, we can sort of keep up with where the entries are in our matrices. Well, what can we do with a matrix? Turns out that a matrix design helps us to solve a system of equations in very much the same way that we solved systems earlier. That is, now notice this is the augmented matrix that comes from the system that we just talked about. And what we will attempt to do, and notice that this is a very similar arrangement to the arrangement that we considered in dealing with systems of equations. If we put an equal sign in these 3 positions, and we put the x's and the y's and the z's here, we would have exactly the same layout that we had earlier for systems of equations. It may make some sense then that in this matrix format, to solve the system, we are going to do much the same kinds of operations that we did earlier. That is, we can take one row and swap it with another row. We can multiply within a row, and we can add and subtract various rows. So let's perform those operations and solve the system. Now, what we're trying to do is what we tried to do earlier. That is, we'll transform this matrix into one which has a 1 in this position, zeros in these positions, then a 1 in this position and a 0 below the 1, and then a 1 in this position. And once we've arrived in that condition, we can then go back into the system of equations format and perform a back substitution to get our solutions. Here's what I'm talking about. Suppose we want to cause a 0 to occur in this position. That is a 0 right here. And I'm thinking of it here because I'm considering what operation needs to be performed to accomplish that task. Well, if we simply add these 2 rows, then we'll get a 0 in this position. All right, let's do that. But let's indicate what we're doing out to the left. We're taking row 2 and we're adding row 1. So adding the 2 rows, we get a 0 in this position. Adding the 2 rows, we get a 1 in this position. Adding these entries, we get 3. Adding, we get 5. Now let's decide what needs to be done to cause a 0 in this position. by looking at the 2 and looking at the 1. We're playing these two rows against one another. What we'll need to do is take row 1 and multiply in row 1 by -2. So it'll be -2 times row 1 plus row 3. So -2 times 1 is -2, plus 2 is 0, giving us a 0 for this entry as expected. This is what we were trying to accomplish. But we need to continue this pattern throughout this row for the remaining entries. All right, -2 times -2 is 4. With -5 is -1. All right, -2 times 3 is -6. With 5 is -1. -2 times 9 is -18. With 17 is -1. All right, now we have accomplished a 1 in the upper left-hand corner and zeros below. We've accomplished a 1. You see, we want 1s along this diagonal and then zeros below the 1s. We want that kind of pattern to be established so that we can accomplish easy back substitution. All right, we need a 0 in this position. What we'll do in our next step is we'll bring down the first row. You see, we're only operating on this row in order to accomplish the 0 in this position. These two rows are fine, so we'll simply bring them down. All right, now once done, we decide what operation we'll perform with these two rows in order to accomplish the 0 here. And the operation, of course, is addition. So we're taking row 2 and adding row 3. Just adding the two rows. Of course, adding the zeros, we get 0, and that's a trivial matter. Adding these, we get 0 as expected. 3 with -1 is 2, and 5 with -1 is 4. Our next task would be to cause a 1 to appear in this position because we want 1s along this diagonal. And in order to accomplish that, we'll take this row and divide by 2. Before we do that, though, let's bring down these other two rows. Let's do that up here. So I'm simply bringing down the 1, -2, 3, and 9. Then, well, let me leave a bit more space here. And 0, 1, 3, and 5. Now, I'll indicate the operation being performed here. I'm simply taking row 3 and dividing by 2. And dividing through by 2, I get the zeros and the 1 here, and the 4 divided by 2 gives me a 2 in the lower right corner. Now, at this point, we can stop our matrix operations procedure, and we can go back into this or look at it as a system of equations. That is, this first row corresponds to 1x minus 2y plus 3z is equal to 9. Notice I'm writing the z now with this little slash through the middle because I have the fault of writing 2's like this occasionally. And to differentiate z's from 2's, I write the z like that. All right, let's see. In the second row, I have 0x, 1y, 3z is equal to 5. And in the last row, I've got simply 1z is equal to 2. So this tells me that z is equal to 2, and now the back substitution is particularly easy. I can even do it in my head, perhaps. If z is 2, then I have 3 times 2, 6. Subtracting 6 on both sides, I find y to be -1. If z is 2 and y -1, then I can pretty easily back substitute these into equation 1 to figure out x. Well, let's do that. If z is 2, then we have 6 in this position. If y is -1, -2 times -1 is 2. 2 plus 6, 8. Subtract 8 on both sides, we find that x then is 1. So the ordered triplet 1, -1, 2 solves our system of equations. That is, this solution, of course, makes all three of our original equations true. Now, there is another process by which we can come to a solution. This is called Gaussian elimination, what we have done so far. Another process would involve staying within the matrix format and creating situations where there are zeros in these three positions. Zeros here, you see. If these were all zeros, understand what that implies in the system of equations format. If that's a zero and this is a zero, we have 1x is equal to some number. 1y is equal to some number if that's a zero. And then z, of course, is 2. Well, in the matrix format, we can accomplish that by doing this. We'll work from the bottom of the matrix up. That is, the last row is in precisely the condition that we want it to be in. That is, we've got a 1, a 2. That means that z is equal to 2. No additional work needs to be done. Our work is done above this 1. Now, it's important to understand conceptually how we're approaching the matrix type of solution for a system of equations. We work essentially from the top of the matrix down during the first part, that is, during the part where we're trying to accomplish 1s along the main diagonal and zeros below these 1s. Now, after that, our concept is to work from the bottom of the matrix up. That is, we're working from the bottom row and we're operating on the upper rows to accomplish the zeros above the 1s. All right, let's decide what needs to be done for a 0 to appear in this position. Well, for this entry to be a 0, we'll have to multiply the 1 times -3 and then collect. So we'll take row 3 and multiply by -3. So it's -3 times row 3 and then add row 2. Now, this is a particularly easy situation to deal with because of the zeros that appear here and here. Because -3 times 0 is 0, and -3 times this 0 is 0. And when we add to the entries above, we get the same entries that were there to begin with. So we simply bring these down. Once you get used to this, it's bring down, and this, by virtue of what we have described here, will necessarily become a 0. So all of the action is in the constants, you see. We just have one real thing to consider here, and that's what occurs in this position of our matrix for that entry. Well, let's see. -3 times 2 is -6. -6 plus 5, -1. All right, now let's decide what needs to be done. Notice we're working our way up. What needs to be done to cause this entry to become a 0? Well, same idea. We're playing these two rows against one another. So we'll multiply in row 3 by -3. So it's -3 in row 3 and add row 1. And once again, since these are 0 entries, we simply bring down the 1, the -2. And this will become a 0. And all of the true mental strain that we have here is here in the constants. So let's see, -3 times 2 is -6. -6 with 9 is 3. All right, we're almost done. Just one more step and we're all finished. The last two rows now are in the condition that we would like them to be in. That is, we have the 0, the 0, the 1, and a constant. The 0, a 1, a 0, and a constant. You see, so let's bring those down. Now let's decide what needs to be accomplished in order for this entry to become a 0. And we're playing these two rows against one another. That is, we're going to perform an operation on row 2, and we're going to collect with row 1. So it'll be 2 times row 2 and add row 1. So let's see, 2 times row 2 and add row 1. And in doing that, we have a 1, a 0, a 0. You see, I really am not even considering the 2 times 0 plus 1. Once we do this just once or twice, we realize that what's going on in our first 3 entries is rather trivial. We just bring down the 1. This becomes a 0 because of the way we set it up. This 0 occurs trivially. And all of the activity, again, is with the constants. So let's see, 2 times row 2. That's 2 times negative 1 is negative 2, plus row 1, that's the plus 3, is 1. So now notice what the system is telling us. It says that x, no y's, no z's, x is simply 1. Y is negative 1. And z is 2. So again, we get the same ordered triplet that we had before. Now, some might say, well, this is tougher than back substitution, but when the numbers get a little bit larger, you may find that this is a preferred solution than the back substitution is. This is even easier than that is. And this method, by the way, taking the matrix all the way to a condition of 1s along the main diagonal, 0s below, 0s above, and these constants, taking it to that point is called Gauss-Jordan elimination. Here's a system of 4 equations in 4 unknowns. Now we'll use a matrix type of arrangement to help us solve this system of equations. The system could be solved using previously learned methods. That is, we could use the method of elimination, which we talked about in another chapter, but the proposition would be very, very cumbersome. You may think that the matrix idea is rather cumbersome, but really dealing with all of the x's and y's and z's and w's in this case and the equal signs makes it even more so. So the matrix format is a way of streamlining our efforts toward solution. Here's how we would begin this problem. Now we want to set up a matrix, and the first item of business sometimes is to simply place the variables in the various columns. You see, lining up the w's and the z's and the y's and the x's. Sometimes equations are all jumbled up in that way and have to be placed into this order before even going into the matrix format. Well, these are all in sort of a row type arrangement with the constants placed on the right side of the equations. So let's go into the matrix format. Now, in order to do that, we simply write down the coefficients involved for the x's, the y's, the z's, and the w's. Here I have no x's in the upper left-hand corner, so I'll enter a 0 for that position, and then a 1, and a 2, and a 1. You see, and down the y's, I've got a 1, 2, 4, negative 4. Down the z's, 1, negative 1, 1, negative 7. And then the w's, negative 2. No entry here means 0 w's, you see, for that one. And then negative 3, negative 1. The constants, negative 3, 2, negative 2, negative 19. What we wish to accomplish here in this matrix format is an arrangement in which a 1 appears in this entry, and zeros below that 1, and then a 1 here, and a 1 here, and a 1 here. That is, 1s along this diagonal, and zeros below those 1s. Well, there is some process here, some procedure that we need to be aware of. We can divide our this whole idea into various little tasks. First task would be to place a 1 in this position. The next task would be zeros below that 1. After that, a 1 here. After that, zeros below. Then a 1, and then a 0, and then a 1. You see, in taking it just in parts like that, just a step-by-step idea, we can keep things relatively organized. All right, first idea then is to place a 1 in the upper left-hand corner. That can easily be accomplished in this problem by swapping these 2 rows. Actually, we could swap these 2 rows if we wish to do so, couldn't we? Now that leads us to a situation or a conclusion here that our format for the matrix in each step is not a unique one. That is, 2 people might have a different matrix in the third step and yet still get correct solutions. So there are several roads that lead to success here. All right, what I will do is swap these 2 rows to accomplish the 1 in the upper left-hand corner. And I'm indicating that up here. All right, I indicate the operation that's performed, and then I perform the operation. And I've just swapped the top 2 rows, and it's a relatively trivial thing, so I'm not showing it or writing it all out, just swapping the rows. All right, now what we wish to do is work our way down. That is, we want to cause zeros to occur in these three entries below the 1. That's our next task. All right, a 0 already appears here. So these two rows are all right. They're not to be operated upon, so I have brought those two down. Now what we do is consider what operations need to be performed in order to cause a 0 in this position. What we'll do is play these two rows against one another. You play the 1 against whatever entries are below in order to accomplish the 0. So we'll multiply times the 1, you see, and then add with the 2 in this case. So we'll multiply -2 times the 1, or actually it's -2 times all of the entries in row 1, and then add row 3. Let's indicate that here. -2 times all of row 1, and then add row 3. That will cause a 0 in this position. But we have to perform the same kind of operation throughout the row. All right, let's see. -2 times 2 is -4, with 4 is 0. -2 times -1 is 2, with 1 is 3. -2 times 0 is 0, with -3 is -3. -2 times 2 is -4, with -2 is -6. You may be noticing now that it is important to concentrate well and to not make errors in your entries. Space the items in each row far enough apart so that there is a distinction, and write large enough to where there is no confusion about the digit that makes its appearance in any position. The reason for writing the operation to the left of a row that's being operated upon is that if you need to review the problem, that is, if you discover at the end that there is an incorrect solution and you wish to backtrack, then you can backtrack much more easily by understanding the operations that you were attempting in each position of the problem. So it makes checking much, much easier. All right, let's decide what we're going to do here. Well, we need to simply take the difference of the two rows. So we'll multiply in one row by -1 and add the other row. Traditionally, we operate on this row and then add the row below. So let's do that. It's -1 times row 1 and then add row 4, which will give us, let me drop this just a bit here, we'll get a 0 in this position. That is, -1 times 1 is -1 with 1, 0. Now, -2 with -4 is -6. Negative of -1 is 1, with -7 is -6. The negative of 0 is 0, with -1 is -1. The negative of 2 with -19 is -21. All right, so now look at what we have before us. We've got a 1 and zeros accomplished. Our next task would be to cause this entry to be a 1. It's already a 1. That task is now finished. The next thing we wish to accomplish is zeros below that 1. This one is already a 0. All right. So there is no operation that needs to be performed and that will change these three rows. So I have brought those three rows down to this position. All right. What we have before us then is that we wish to change this entry to a 0. Now, it's important to understand that we're going to play these two rows against one another. Some might say, well, why not simply multiply in row 1 by 3? 3 times 2 is 6, and add the two rows. If we did that, notice that we would need to do that same type of operation to this entry. You see, 3 times 2 is 6, with -6 would give 0, but 3 times 1 is 3, with 0 would give a 3 right here, which we don't want. So in order to avoid having a non-zero entry in that position, we'll play these two off of one another. Because after all, multiplying times the 0 and then adding the 0 will still cause this entry to become 0. All right, at any rate, we're going to multiply 6 times 1 and add the -6 to give us the entry in this position. So it'll be 6 times row 2 plus row 4. All right, let's see. Of course, we get a 0 in this position. 6 times 1, 6 with negative 6, 0 as expected. All right, 6 times 1, 6 with negative 6, 0. 6 times negative 2 is negative 12 with negative 1 is negative 13. 6 times negative 3 is negative 18 with negative 21 is negative 39. All right, let's decide what we need to do next. We have a 1, zeros, a 1, zeros. Next task, a 1. All right, to accomplish the 1 in this position, we can't very well play these against one another. You see, take a difference or multiply or whatever, but we can operate within this row. Now notice that it's real easy here to divide through by 3. So let's perform that operation. All right, we'll bring down the first two. Normally what we would do is bring down the first 2 rows, then indicate the operation and divide through. Now since this is a relatively trivial operation, I have performed the operation up here. So here are the top 2 rows that we bring down, and then we indicate that we're dividing through by 3 in row 3, and we get these entries. We get the 1, the negative 1, the negative 2, and we bring down this 4th row. All right, now let's decide where we go from here. Notice that we're almost there. We almost have this main diagonal as being all 1s. We need a 1 in this position. So we decide then to divide through in row 4 by negative 13. We'll indicate that here, row 4 divided by negative 13. Dividing by negative 13, we get a 1. Divide negative 39 by negative 13, and we get 3. Now, this is a significant point in our problem. We have arrived at our echelon form. Now, echelon form simply refers to this stair-stepped configuration here in this form of our matrix. And we arrive at this stair-step or echelon form by using the method of Gaussian elimination. We're going to continue our problem now to an answer, and our answer method can take a fork in the road here. We could go to an equation, a system of equations kind of format, because after all, this last line, this row 4 in our matrix format is really 0x plus 0y plus 0z plus 1 y, excuse me, 1w is equal to 3. So w is 3. Now, if w is 3, we could back substitute that information into the next equation and find z. And then with z and w, we could back substitute, you see, and find y and then x. But another way to proceed is to stay within the matrix format and continue to reduced echelon form by using the method of Gauss-Jordan elimination. And that's what we're going to do. All right, in order to do that, what we want to accomplish is, now notice the 1s along this diagonal. What we want to do is cause the entries above those 1s to become 0s. And then the matrix will be telling us the solution. Well, let's see. Let's decide what needs to be done to cause this entry and this entry and this entry to become 0s. We'll bring down the last row. See, we've brought down the last row, and just for emphasis, I have written down the entries along this diagonal, the 1s and the 0s here, that we've already accomplished, and we're really simply working above the 1s at this point. Well, to cause this entry to become a 0, we'll simply add the 2 rows. That is, we'll take row 4 and we'll add to row 3. So we'll indicate here row 4 plus row 3. And the 2 rows added here give 0. The 2 rows added here give 0. See, these are trivial operations. The 2 rows here, adding these 2, again, it's fairly trivial. It's simply 0 as expected. So adding these 2 now, the 3 with negative 2, gives us 1. All right, deciding what to do to cause this entry to be 0, we play it off of row 4. So we'll multiply 2 in row 4 and then collect with row 2. So 2 times row 4 plus row 2 is what we're doing. And again, the situation is trivial. We'll end up with a 0, a 1, which is the entry that was there before. Because after all, 2 times 0 is 0 plus 1 is 1. You see, that entry just stays the same. This entry that we're picking on becomes 0. And now all the activity is in the constant column, you see. All right, 2 times row 4, that's 2 times 3 is 6, with negative 3 is 3. All right, now how do we cause, what do we do to cause this entry to become 0? Well, nothing. We don't have anything to do. We simply bring this row down because it's already in the condition that we're after. So we'll bring down the 2, the negative 1, the 0, and the 2. Now notice where we are in our process. We have caused all of these entries to become 0. Our next job is to cause these 2 entries to become 0. So now the bottom 2 rows are just fine, so we'll bring them down to the next step, and then we'll decide what to do. Now let's refer here just for a second to understand what we're going to indicate up there. We're going to indicate to cause this entry to be a 0. We'll have to play these 2 against one another. We want to take negative 1, or the negative of row 3, and add with row 2. That's what we'll indicate above. And to cause this entry to be 0, we'll simply add the 2 rows. That is, we'll add row 3 with row 1. All right, let's begin up here. We bring down the lower 2 rows because they're in fine shape. Now we indicate what we're going to do here. It's the negative of row 3 plus row 2. All right, the negative of row 3 plus row 2. All of these entries now, there's no big deal in all of the entries through here. All of the activity is here with the constant. So it's the negative of 1 plus 3, which will give us 2 for that entry. So here's the important one, and the other entries are relatively predictable. We get a 0, which was here before, a 0, a 1, and the 0 that was there before. All right, now for row 1, we simply add with row 3. That is, we take row 3 and add row 1. Now let's see what happens. When we add the 2 rows for the first entry, we get a 1. For this entry, we get a 2. Just adding these 2, you see. For the entry here, we'll get a 0 because we're adding these 2, and then a 0. So again, all the major activity is with the constants. 2 and 1 give 3 for the constant. Now, these bottom 3 rows are in good shape, and the only thing we're attacking now is this entry. We would like this entry to become a 0. So what we'll do is play it off of row 2. We'll multiply negative 2 in row 2, and then add row 1. All right, this will cause a 0 for this entry. The other entries are trivial, and the constants is where we want to concentrate our efforts. Negative 2 in row 2, and add row 1. Negative 2 times 2, negative 4, plus 3, negative 1. And now this is reduced echelon form, and the matrix really tells us the answer or the solution set to our problem. We know now that x is equal to negative 1, y is equal to 2, z is equal to 1, and w is equal to 3. So this is the solution set then for this system of equations. When we talked about systems of equations in a previous chapter, we discovered that there were several kinds of solution sets possible. That is, there were consistent systems that were composed of either one single solution or an infinite number of solutions. And there were inconsistent systems where there was no solution possible. Let's examine those odd situations now. Suppose we have this little system of equations, and we wish to solve by using a matrix. Now, all we want to notice here in this discussion is the appearance of the matrix that the matrix takes on to generate the idea that we have something odd that's going to occur with our solution set. All right, so just notice this. We go from the system of equations into matrix format. Now, we wish to put our matrix into our echelon form and perhaps then go on to reduced echelon form, we're thinking. But at any rate, we want this entry to become a 1. To accomplish that, we'll multiply through by negative 1. In doing so, we get these entries in the top row. All right, now we wish for this entry to become a 0. So we'll multiply equation 1, or excuse me, row 1, by negative 2 and add to row 2. So negative 2 times row 1 plus row 2 gives us a 0 here. But look at what else happens. Negative 2 times negative 2 is 4. 4 with negative 4, 0. Negative 2 times negative 1.5 is 3. 3 and 3, 6. You see, what has occurred here is that we have zeros in both of these entries and a 6 here for the constant, emphasizing the idea that that is a constant and these are the coefficients of variables. It would lead us to the idea that we have no x plus no y is equal to 6. You see, all of the letters have gone out of the equation and we have a false statement. That is, we have 0 is equal to 6 for the equation that corresponds to this row. Now, when that occurred before in systems of equations, that is, all the letters go out and we have a false statement, we determined that we have an inconsistent system. That is, there are no real solutions in the system of equations. And that's true here. So we're looking for the situation where all the letters go out and we have a false statement. All right, here's one where we have an infinite number of solutions will occur. Let's run through right quick. Here's our system of equations. We set up the matrix format. All right, we have a 1 in the upper left-hand corner. Next task is to cause these two entries to become zeros. I've determined here that in this row we need to take the negative of row 1 and add to row 2. Negative row 1 plus row 2 gives us 0, and then negative 1, 3, and negative 2. In order for this entry to be a 0, negative 2 times row 1 plus row 3. So negative 2 row 1 plus row 3 gives us 0, negative 3, 9, negative 6. You see, at this point, this looks very normal. We don't suspect that anything funny is going to occur, but it certainly will. All right, so we have a 1 and zeros. Now we wish for this entry to become a 1, and for that to happen, we'll multiply through by negative 1. Let's do that up here. So we've indicated the negative of row 2, or negative 1 times row 2, gives us 0, 1, negative 3, 2. The sign simply changed here, and I brought down the last row. All right, to cause this entry to become a 0, we'll multiply in row 2 by 3. 3 times row 2 plus row 3 will give us the 0 entry. Now, here's where we pick up the problem. All right, 3 times 1 is 3, with negative 3 gives 0 for this entry. This is a bring-down situation here. All right, 3 times negative 3 is negative 9, with 9 is 0. The zeros all the way across again for the coefficient portion of the matrix. Then 3 times 2 is 6, with negative 6, 0. Now notice zeros all the way across. Now the interpretation of this row in equation form is that we have 0 is equal to 0. We have no x's, no y's, no z's is equal to 0. Well, that's a true statement, you see. So all of the letters have gone out, and we get a true statement. Well, that was what occurred in systems of equations before, which led us to the idea that we have an infinite number of solutions. Now we might consider how we display that infinite number of solutions. What's one set of solutions? If there's an infinite number of them, just name one. Well, here's how we can generate all of those solutions if we wish to do so. Understand now that our matrix leads us to this new system of equations. We have x plus y minus 5z is equal to 3. That's this equation. Then we have 0x plus 1y minus 3z is equal to 2. That's this equation. And this one is trivial. It's simply nothing. So we simply, our system is really 2 equations in 3 unknowns. And here is that system. Now what we do with this is this. We take either equation, actually the one involving the 2 letters is the one that we want to deal with here, and we solve that equation for 1 letter. Well, it's pretty easy to solve in this equation for y. We simply kick out the negative 3z. So y is 3z plus 2. Now, solving for 1 letter in terms of the other allows us to begin to set up an ordered triplet as our solution set. All right, let's let a real number A, any old real number, stand in for Z. Z being the third component now of an ordered triplet. So we'll come up over here, and if A stands in for this third component, the second component, the Y, you see, is simply given by the equation that we have here. If Z is A stands in for Z, so Y then, the second component, is 3 times A plus 2, 3A plus 2. All right? Now what about X? What about the first component? Well, we can find that by using our other equation and substituting just a bit. Now Y, you see, the second component here is the 3A plus 2. And Z, of course, the third component is A, so this is minus 5A. All right, now, collecting, performing operations, solving for X, we find X to be 2A plus 1. So the first component in our ordered triplet is 2A plus 1. All right. This gives us then a way of generating as many answers for our system of equations as we would like. And one of them, for example, could be found by letting A be, let's say 2. If A is 2, then 3A plus 2 is 3 times 2, 6 plus 2, that's 8. And 2 times 2, 4 plus 1, 5. So the triplet 5, 8, 2 will solve the system of equations. And by substituting these three values, these values of X, Y, and Z, into our original set of equations, we would find that this set makes the system true. If we let A be 0, you see 0 would be here, 2 would be in this position, 1. So 1, 2, 0 is another triplet that solves the system, and we could generate an infinite number of solutions in that manner.